Welcome to Dr. Tarazi's Math Site. This video is one of a series covering the released Ohio State math questions between 2017 and 2023. Geometry makes up almost one-third of the test questions. Standard 8.G.4. Understand congruence and similarity. Understand that a two-dimensional figure is similar to another if the second can be obtained from the first by a sequence of rotations, reflections, translations, and dilations. Given two similar two-dimensional figures, describe a sequence that exhibits the similarity between them. Include examples both with and without coordinates.
Hello and welcome. Here is what you need to know before we get to the examples.
Before watching this video, it is highly recommended to watch the previous video, Math Grade 8, Standard 8.G.1, Matching Parts of Congruent Figures. Here is the link to it.
To make the most of these videos, I suggest pausing the video when you see this button, solving the problem, and then resuming the video to check your answer.
Example 1.
Yes, here we have two similar figures, parallelograms EFGH and PQRS. And the question is, which sequence of transformations can be performed on EFGH to prove that the parallelograms are similar? In other words, what are we doing to this small figure to make it this one, to become this one? Now, obviously, when you see a change in the size, definitely there is a dilation. Excuse me. So there is a dilation for sure. Now, here they're giving you options. You can read these options. A reflection across the x-axis, then a dilation by a scale factor of 3. So that is a possibility. We'll come back to it. Option B, a reflection across the x-axis, and then a dilation by a scale factor of 1/3. Now here's the problem. From here to here, the scale factor must be greater than 1 because you are enlarging the figure. You're making it bigger. So this option is not correct. C, a 180 degrees clockwise rotation about the origin and then a dilation by a scale factor of 3. Yeah, that's a possibility. So we will come back to it and see if that's the correct answer. The last option is a 180 degrees clockwise rotation about the origin and then a dilation, excuse me, a dilation by a scale factor of 1/3. That's also not acceptable because the scale factor must be greater than 1 for this to become this. So that's also cancelled. So now we have two options, either this one or this one. So let's try this option and see what happens. So let's try option A. Here's my figure, original figure. These are the coordinates of the points, of the vertices. So obviously E is 1, 4, 1, 4. F is -2, 4, -2, 4, etc. Now we're going to do a reflection across the x-axis. So it's reflected across the x-axis. Okay, that's more like folded across the x-axis. So this point here is going to be here. And this point here is going to be here. And this point here is going to be here. So these are the coordinates of the reflected figure. Now, when you look at this and look at this, you see that is a very, very possible that this was enlarged 3 times, a dilation of a factor of 3. So if I put the coordinates of PQRS and you see that each coordinate is multiplied by 3. See, 3 minus 12, minus 6, minus 12, and so on and so forth. So that for sure, this is a dilation by 3, and then the answer is A. Now, if you want to see why the C is not a good answer, let's see what happens. If I want to do 180 degrees clockwise rotation, by the way, 180 degrees, whether it's clockwise or counterclockwise, is the same, okay? About the origin, and then a dilation by a scale factor of 3. So let's see what happens here. Here's my EFGH. So I'm going to do a rotation of 180 degrees. So which means all these are going to change their signs. Now, if I will get this here. Obviously, you cannot dilate this to get this, okay? So if I put PQRS here, and you notice that this one is not 3 times this. See, this one minus 6 is not 3 times 2. So obviously that is not a dilation.
Example 2.
In this example, the coordinate plane is shown. Ted draws triangle MNO in quadrant 3 of the coordinate plane. He then applies 2 transformations to the triangle. First, the triangle is reflected across the x-axis. So that's important here, the word reflected. Keyword. The other one is then the triangle is dilated by a factor of 1/3. Okay, so there's a dilation here as well. So this is quadrant 1, 2, 3, 4. Okay, going that counterclockwise. So, and then you have a few questions here. Which statement is true about triangle PQR? Triangle PQR is congruent to triangle MNO? Absolutely not, because when you do a dilation, you will not get a congruent result. This one is not even good either. So if I draw and just give yourself a small example, I mean a very simple example. Here's a triangle. So I'm going to do a reflection across the x-axis, then a dilation of 1/3, which means it's shrinking it. So that's the end result. And you see that they can't be congruent. They're similar for sure, but they can't be congruent. So A is not an option, B is not an option. Then you have a choice between C and D. Triangle PQR is similar, yes, to triangle MNO. And in quadrant 4, is this one here? No. So I'm only left with this option, which is correct. PQR is similar to triangle MNO, and in quadrant 2.
Example 3.
A horizontal line M is shown with 2 similar triangles ABC and DEF. ABC and DEF. How can triangle ABC be transformed to result in triangle DEF? Even before reading any of these options given to you, there is a dilation for sure, because we came from here to here. So there's a dilation. So if you look at this reflection across, that's not an option at all. Here, 90 degrees rotation about point C. No, there is a dilation for sure. Now, if you look at a dilation, then translation to the right. If I do a dilation, that means I made this a little bit bigger and I moved it to the right. That's it. This one, a dilation, then a reflection across a vertical line, that's impossible. I will not give you this.
Example 4.
2 triangles are shown. What transformations can be used to show that triangle LMN is similar to triangle PQR? Now, again, since this shrunk to this, we must have a dilation. So when you look at these options here, reflection, translation, that's not a good option. Rotation, dilation, we will come back to it. Translation, rotation, no. There must be a dilation. So what I did here is it says reflection, translation, the dilation, reflection, dilation and reflection. It will not give you this. So what I did here is I drew this triangle and I rotated it a little bit to the left. Then this is exactly looking like this, except that's bigger, obviously. So we rotated this and then dilated it. So rotation, then dilation, I can get this. You can also do dilation first, and then rotation. You can also get to this triangle.
Example 5.
This one is really simple. Parallelograms A, B, C, D, and W, X, Y, Z are shown. What transformation is used to show that the parallelograms are similar? Now, obviously, when you have a big figure and a small figure, you must have a dilation, okay? So the reflection is not a good, rotation is not a good, translation is not a good. Obviously, the answer, very straightforward, is dilation.
Example 6.
This example is not really nicely worded. So it says two quadrilaterals are shown, these two here. Brian uses two transformations to show that quadrilateral JKLM is similar to quadrilateral WXYZ. Obviously, they're similar. So again, to go from here to here, you must have a dilation for sure. So you have dilation here, you have some dilation here. So this one is not going to be a good answer at all, okay? Okay, now let's look at the rotation and dilation. If I rotate this and then dilate it, we'll not get to this for sure. Dilation and reflection. If I do this as a dilation, that means I make it bigger, and then I can reflect it across a line like this, I can get this. And also dilation and translation will do the same work as well. If I do a dilation to this, make it bigger, and slide it, I can get this too. So obviously here, I think there is two possible answers to this question.
Thank you for watching. If you would like to have a copy of the PowerPoint presentation, please leave your email address in the comments section, and we will be happy to email you a copy.
Thank you, and see you soon.
Thank you for watching. More videos to come. Please subscribe.